All right, good afternoon. I'm just going to fill in some odds and ends. None of this is really going to be necessary for the physical chemistry class, but they're pretty cool stories, and they also will help 3422 students write about some question. I've given you the assignment, write about anything. Maybe it could be about one of these topics. So we covered this article, and I just want to say this article has 8 different outreach activities. I always like collecting these, and I do have the actual article that says specifically what these things are doing. Just send me an email if you want that. These 4 of the 8 are actually very closely related to this particular chapter, and I can see ideas for all of these that you could write questions about, and also maybe someday you want to try it. Some of them are with more ordinary materials. Now here's another couple of ones. I just want to say that this particular article has a whole bunch of these outreach demonstrations. You can actually do the thermite reaction. I've never been brave enough to do that. The traffic light bottle looks cool. It changes those different colors. And then I've heard of the blue bottle experiment, which actually changes from blue to colorless, I think. I've actually done the cobalt blue as well. So these are the kind of things you can do to show people what chemistry is about. You can also write problems, quantitative problems, that are built around these kind of cool equations. So, one of the things that happens is, why do batteries run out over time? And the reason why they run out is they make these branching structures, which are actually some of the topics of other chapters in The World from Dust. And it includes the idea of entropy is why these sort of beautiful branching structures happen, because the solid is spreading out. The spreading out nature, it can spread out most maximally in these particular crystalline conformations. As it solidifies, which is a decrease in entropy, it's also like maximizing its entropy of solidification by branching out. And so I just think that's cool. You can see how if you have galvanic or electrolytic cells, you can actually have the copper and silver actually form similar branching structures. Lead and tin can form they're more like each other. They're more angular branching structures. And the reason why they do this is their chemistry. But it's a consequence. These branching structures are both a cause and effect of the battery wearing down. The battery's energy is stored in 2 separated compartments. Those compartments start to break down. Even if you have a rechargeable battery, the structures of the solids will start to break down and spread out. And you can see this, you notice that if you have the direct electrochemical reaction, like the zinc-copper displacement reaction, you will have something like this forming. And depending on the conditions, you can have it be more or less branched out. But it's kind of cool to think about, why do these branches form in this way? Copper is A, B is silver, C is lead, and D is tin. And E is a different kind of copper. And so if you actually look at a battery once it's spent, it will have formed this kind of spread out. What's happened is you have 2 compartments, and the electrons have moved from one compartment to the other, and they have formed the more stable material. Once they have moved to a point of equilibrium, you no longer have electron flow, and the battery is dead. Now the thing is, you can tell a dead battery physically different from a live one. You don't think of the electrons, and technically the electrons have a tiny bit of mass, but there's not enough mass stored in the form of electrons to make a live battery heavier than a dead battery. And also, think about it, the electrons are actually moving from one place to another. They end up in the battery in a sense. They just end up in a different place. All that is to say, you can have physical changes that happen in the battery that you can measure. And one of the ways you can measure whether a battery is dead or not is by bouncing it. It turns out that these physical changes, when the battery is discharged, will change its elasticity. And you can actually talk about how you can measure whether it's live or not, or even how much charge is left, by how high it bounces. Talk about this, you have to talk about what batteries are made from. They're made from these 2 half reactions put together. It's zinc and manganese, and a manganese oxide actually. And it turns out that a lot of the cheap alkaline batteries will be like this. And from their name, you can tell it's alkaline, right? It takes place in a basic environment. And so these are the two reactions. You flip one around and you make, I don't have the voltages, but I believe it's going from the zinc to the manganese, but don't quote me on that. You'd have to look at the actual things to see where they would, which ones they would be. I also say that because they are alkaline, and an alkaline condition would actually help this to move forward if the bottom was reversed. We'll see if I'm right about that. You can look it up. The main thing I don't have to look up is the fact that the dead batteries will bounce differently. This is a battery, and this is the current it delivers over time. It's interesting that it seems like batteries die all at once, but you probably notice they sort of do peter out a little bit. They give less current. And if you look at current versus time, yeah, it's not a perfectly sharp graph. It sort of slopes down, and then it goes way down, and then it's flat, and then you can maybe squeeze a little more out of. So it's a little S-shaped, but you do have this thing. When you run it all the way out, the battery is completely dead, and all the electrons have moved from the left to the right, the way that we represent the cell. And so they measured the bounce height. They actually would bounce it, and they would see the maximum possible height you would get after dropping them from a certain height. We could calculate the MGH energy of that, but that's another calculation. And what they did is they measured charge delivered versus the COR. What is COR? I think it's the bouncing of it. Yeah, it must be the height of bouncing. So if I'm reading this correctly, it seems like they bounce higher when they have more charge delivered. They become more elastic when their electrons have been discharged, and they're more stiff when the electrons have not been discharged. And maybe that's a consequence of entropy as well. They were able to measure the percent of zinc remaining. The zinc gets consumed when it gets turned into the other, it gives off its electrons. So I'm actually going to see if I'm right. Yeah, the zinc is giving off its electrons because it's being consumed, and they're measuring how much zinc metal is left as it goes along. So I was right. You do flip over the bottom. Good. It's nice to be right. And you see that the charge delivered and the percent zinc is actually following a straight line. And that's the end of that particular story. They actually were able to measure it, and the batteries will bounce higher. So maybe if you don't have the chance, if you have a bag of batteries and you want to know which ones are still intact, maybe you can try bouncing them. Although I'm not sure how it works for, say, rechargeable batteries. I'm not sure how you have to get a paper and do the science for that. But maybe that's a project for you sometime. Here's another paper. This is kind of complex, but it's cool because nanoparticles, you can develop those. They're basically metallic, so they're zero charge forms, mostly. But they are formed in very small particles that are like nanometers big. And these will have distinct properties, including colors. And so what you have is you have you can make these in different ways. One of the ways in which you can make it is a variation of the copper-zinc displacement. Instead of zinc, you're using silver, and you're using silver nanoparticles to sort of, you're using the copper to sort of help you make the nanoparticles. It's actually a little more complex. I haven't completely gotten into it. You can look more into it if you want, because I'm giving you the paper right here. But here's the idea, is that you have the copper ions, and you have nanoparticles inside the copper. And then you form silver nanoparticles from that. They aggregate, and then they precipitate out to the bottom. And you see in B on the top, you have the copper solution, but you have silver nanoparticles that have incorporated some of the copper on the bottom of the solution. And so it's kind of cool, and like I said, it's kind of complex, but the important thing is that making the nanoparticles is a different color than if you just mix the silver nanoparticle suspension with blue coloring. There's something different going on, and that's shown because if you just take the silver particle suspension, which is B in both of the cases here, and you mix it with the blue A, which is just blue dye on the bottom, you see that you get just sort of the colors don't really mix. You end up with this sort of yellow, green, and blue sort of material at the same time. So A plus B goes to C. A plus B, if A is the copper sulfate, and if that's the reason why it's blue, the copper will actually react with the silver nanoparticles, and it will make this black C situation, which will eventually settle out. I believe some of the copper is actually plating out and making the nanoparticles bigger, more insoluble, and also darker. And that's why you get D after you wait. You let them sort of settle to the bottom, and you have nanoparticles that I believe incorporate copper around a silver core. And those particles could have very different properties. So just realize that this shows you're not just mixing colors, you're really doing a chemical transformation. The dark color of part C on the top shows you that something different has happened than just mixing two colors. Part of what's going on is you see that you have the different particles. This is a nanoparticle. It has certain charges collecting at the surface, and there are balances between those charges, and there's lots of cool stuff going on. You can make cool structures, and you can have them test them for chemical properties. This is what chemistry is about. And so over time, you can prepare them, and you can add the copper, and 1 hour later, they will have gotten a lot bigger. The copper will actually cake itself around the silver core. And that's a really cool structure that you can make. It even has a different color. You can detect it that way. You can go all the way to how do rechargeable batteries work, like how do lithium-ion batteries work. That actually was related to the Nobel Prize in chemistry. Getting lithium to work, being able to unleash its incredibly large reduction potential, is part of what the Nobel Prize was awarded for. So you can talk about the different amounts of volts that you can get. You can actually get a 4-volt single cell arrangement with this, which is really amazing to me. And so you can see how lithium has 3 volts by itself. If you combine it with the right thing, you can see how you could get up to 4 volts. So I guess when I said in class that 3 was the max, well, no, it's 4, but it's not going to be much beyond that for the simple situations where you're depending on the element's voltage. If you're depending on the element's voltage, you don't have any elements that have better voltages than lithium, and it's like a positive 3. So you can't get much beyond, positive 4. Maybe there's a theoretical like 5 or 6 volt battery you could make, but I'm really not sure how practical it is. Anyways, you could get into this if you wanted to learn more about how lithium batteries work. I would love to see a question based on that. And finally, you can, when you see battery advances, you can think about them in these terms. There's a cool example. Now, we aren't going to get an element that's better than lithium, but we might get combinations of elements that work better together within the range of what lithium is, and they might have advantages as far as reactivity or lack of reactivity. So that's why there's a lot of battery science that is about combining different metals, combining anodes and cathodes, and seeing what works together well. Because it's not just about the voltage you deliver, it's about the repeatability, it's about the stability over time, it holding the voltage. And there's a lot of other characteristics beyond simply how many volts can I get out of this combination of things. So, battery scientists are always trying new combinations. And there was something where they tried this weird phase of sulfur, and they got a real outlier that it was much better than other things in other phases of sulfur. So they didn't believe it at first, and they checked it 100 times. You get a lot of false positives when you're running a lot of experiments. But they haven't really figured out exactly why this phase of sulfur gives us such much better properties. But it might be coming down in the future that we have lithium-sulfur batteries that come from this discovery. I mean, I haven't heard of it. This happened in 2022, but keep your ears out. Maybe it'll happen. You know, the problem is not voltage. The problem is recycling. Lithium-ion batteries are usually about 2,000 charge cycles. Lithium-sulfur batteries are nice and cheap, and they're safer in some ways, but they only a lithium-sulfur battery won't actually be able to be recharged. But they found out that if they use polysulfides, in particular monoclinic gamma phase sulfur, you can look up the heat of formation for that if you want, I think. It only occurs with a certain phase diagram, but that actually, physical chemistry is really useful to all this. They were able to make this phase at room temperature stably, and so then they were able to use it in room temperature batteries. This is what they know about how it works. It does involve lithium on one end, and then you have the sulfur on the other end. I believe it's the cathode. And they also are using carbon nanofibers to help arrange the sulfurs. And it's just that this battery works really well in the lab. We'll see. I haven't heard of a product yet that is lithium sulfur, but if you hear about it, do let me know because I talk about it in class. So, and I want to, one exercise I was thinking of you doing, I did this verbally in class. I had you each take a different element and basically make a different battery out of it. You can do that yourself. And I can think next year I might have a more interactive class exercise, but we were interactive enough. I'm pretty happy with that. All right, so this leads you to the future. And hopefully this gets you set for being able to understand battery science as we make new discoveries in it. All right, thanks for listening. This was fun dessert for me. And I look forward to seeing you either on Math Day for the 3422 folks or seeing you in lab for 3410 for the group that's going to show up for lab tomorrow, which is not the group that today said that. I'll send out an email about that. So I'll see you either Tuesday, Wednesday, or Friday. We'll see which one it is. All right.